Okay, so welcome everyone. We'll discuss today of micronized powders. And then I will start with this. With micronized powders, we're very happy about it. But then this is not the optimal powder. It will be fluffy, it contains a lot of air, also because of the particle size, but as well because of the micronization process that introduces a lot of compressed air into the process. It will be sticky because it has a high surface area and probably amorphic surface area. Usually it's non-flowing, it will have tendency to aggregate, and it is sensitive to oxidation and degradation. And this imposes a lot of difficulties both in the micronization party, which is either the manufacturer of the API of the material, or the contractor who is doing the micronization for him, or for the client who is using this material. And if you're in any one of these, then this issue is relevant to you, even if you don't have your own micronizer. In order to start understanding the surface area, I will talk a little bit about how a surface area of a crystal is being formed and what are the specific characteristics of that crystal. So first of all, you have to know that during the growth of crystal, it doesn't go in a uniform way, also because of imperfection, but even if it goes perfectly well, it doesn't mean that the surface has to be smooth and nice. We have corners and rugged zones and imperfection, and they are formed because the crystal is actually trying to grow around these area. You can see here, for example, on by the way, these pictures are from the crystallization of organic compounds handbook, and I really anyone has to do with physical properties and crystallization, I recommend this book. You can see here that do you see my cursor, by the way?
Yes, yes.
Okay, thank you. So you can see that when a molecule is trying to adhere to a crystal, to a growing crystal, it goes there pretty much in a way we are building a brick wall. It will tend to stick to an existing molecule already, or even preferably to the place that we have a lot of surface. For example, for that corner of the crystal. So always the molecule will try to adhere to the place where you have the most surface for adhesion, and that is for all of these corners. A special way of that growth is called the screw dislocation, which is described in this picture. You can see here a step that is being kind of deformed from a growing crystal. It means that it was probably smooth in the beginning, but this is formed because of imperfection, but now it is being intensified and grown. So what happens in this phenomena is that all the molecules will go to this step and will kind of go in circle like that. So it means that actually it goes in kind of a circular motion. And you can see here in this same photograph that very typical crystal faces actually includes this screw dislocation growth. You see here these steps or these spirals. And when you look at the SEM in good enough preparation for most crystals, you will see this. So the area of the crystal is not smooth, and all these little places are those that will be damaged during milling and micronization and will turn amorphous. So even if I have a crystal that I don't really break, but I kind of shake it and traumatize it, these areas will get smeared and become amorphous. And of course, newly created surfaces that are created because of the particles breaking will have higher energy, surface energy, and they will be amorphous. Which means that the surface of the crystals after milling or micronization will be more active, and in practical terms, it leads to stickiness. So how do we handle this surface activity? Eventually it will dissipate like everything in nature. The energy wants to go down, but we want it to go down in the right way. So one way is that it will recrystallize and kind of will dissipate its own surface energy, this is what we want. It means that if the particle was smooth was amorphous to begin with, after a while it will be crystalline. And that's what we want. But in many cases, this is not the only mechanism that happens, but also we have high surface energy that is being released by removing this surface by aggregation or particle growth. And this is why in micronized material we will see creation of aggregates, agglomerates, and even recrystallization or polymorphic changes, especially in the first hours after micronization, where we have a lot of energy that wants to be dissipated from the crystal. This will be an exponential process. In the first 24 hours, probably overnight, it will be very high, very quick, and then it kind of slows down as the energy dissipates. And I'm talking about surface energy, but also about electrostatic charges. And in parallel, we have also the deaeration, where the air will slowly dissipate from the material, will go out, and the entire powder will settle in the tank. So, for example, if we'll have a full tank of fluffy micronized material, maybe after 24 hours, we will see that it settles down. When I'm taking a sample from a powder with a spatula, usually you will see that the particles are jumping away from the spatula. And that happens if I sample it right after micronization. But if I do it maybe a few hours later, it will not happen. And this is where the static charges are disappearing. So what we want is that we want to micronize the material to let it age, but in the right condition, like we age good wine, to let it settle, that in one hand it will deaerate and release the static charges and the surface energy, but will not experience aggregation and agglomeration. So the tips I can share with you are these. First of all, before you perform any QC tests for the physical test like PSD or density or surface area, wait 24 hours at least, because your client is going to receive the material probably a few weeks and even months later, and you want your analysis to be identical to his. So since most of the changes will be in the first 24 hours, it would be recommended not to release the material right away, but to wait like overnight or one day until we release it. By the time or between the time you micronize it and you ship it, you want it to rest in a controlled environment, of course not too hot, but also not to avoid from vibrating the drums, because vibration causes a lot of aggregation. And I will show you later also how to pack correctly the material. So we want the powder to stay in the box, in the closed box, in a controlled environment, of course, and to avoid any sharp temperature changes that may increase or decrease the relative humidity inside the powder, that also may lead to changes. In some very sensitive application like powders for inhalation, it is very common to let the aging take 10, even 30 days in a controlled environment before it is being shipped to the client. In many APIs that go for inhalation, the SOP says to let the material rest even up to 30 days. It's very common. And that saves a lot of problem later in the application. Of course, if the application is not that sensitive, then maybe the natural shipping conditions should be enough to promise this aging. So I had this issue with material that was micronized, and also water sensitive, water soluble, which is not a good combination, by the way. Usually we don't micronize water soluble materials, but if we do, if the material is slightly hygroscopic or water soluble, it's not a good combination. But what happened was, imagine this, imagine you micronize your material in your facility, and you have probably a hot Indian summer day. You have probably 25 to 30 degrees, but very high humidity in the warehouse. So you pack the material and it contains, let's say, I don't know, 40, 60% humidity, which is not that bad. Imagine that you ship the material by ship or by air, and it goes for a very cold area, for example, in the airport or flying or in a ship for a long time. And then what you have is decrease in temperature and increase of relative humidity, and you even get condensation. And I made once an experiment. I took a glass full of powder, and I put one drop of water in the bottom of this powder. And after several days, the water kind of had capillary rise and went through all the material, and everything was lumped and became one aggregate because of one droplet. Now, when you open this, again, the humidity is normal, so you don't see that because the water were there, they created the damage and they disappeared. So I would say that you may want to look into your shipping conditions and also to check for sharp temperature changes and humidity, and I will discuss it in a couple of slides down.